are all gathered for your PhD defense. So the PhD has been reviewed by Nicola Papadakis, who unfortunately cannot be there, and by Themis Sapsis, professor at MIT. Otherwise, the jury is composed of Bertrand Chaperon, researcher at IFREMER, Fabrice Collard, who is director at Ocean Data Lab, Lucie Gauthier, who is research engineer at Ocean Data Lab, myself, Etienne Memin, president of this jury, researcher at INRIA, Jacques Véron, who is a researcher at CNRS. And the supervisors of this thesis were Ronan Fablet, a professor at IMT Atlantic, and Amanda Pasquale, professor at UIB. So you can start. We have 45 minutes to present your work, and then there will be questions from the committee.
Okay, thank you, Mr. President. Just can you see my slides?
Yes, perfect.
And the cursor, can you see the cursor?
Yeah.
Okay, perfect. Thank you, Mr. President, for this introduction. I'd also like to thank my advisors, committee members, and all the audience for joining me today to discuss my PhD thesis on data-driven and learning-based approaches for the modeling, forecasting, and reconstruction of geophysical dynamics, with a main focus on sea surface dynamics. So this thesis is conducted within the framework of Agence Nationale de la Recherche as a part of the research project OceaniX, and it was financed by Région Bretagne and Ocean Data Lab, and I was supervised by Ronan Fablet from IMT Atlantic, Amanda Pasquale from INEDER. And I also worked with within a very close collaboration with Dr. Fab and Lucie Gauthier from Ocean Data Lab, and with Bertrand Chaperon from IFREMER, with the main goal of investigating artificial intelligence technique in order to extract models that can be useful for forecast, simulation, and data assimilation applications of geophysical dynamics. So quick overview of what we'll be going through, at least for this presentation today. I'll start with introducing the general context of this work. Then I will present the concrete problems that we want to solve regarding the modeling of ocean surface variables. Then we'll move to kind of a more technical part of the presentation where I present some of the tools that we developed during this thesis, and I will end up with a conclusion and some perspectives. Okay, so geosciences refers to a global and comprehensive study of the Earth from its nucleus up to space. It englobes the study of geology, the seas, the atmosphere, and the climate, with the primary goal of obtaining a deeper understanding of our planet in order to better survive, for example, extreme atmospheric and climatic conditions, in order to learn how to use our planet's resources, and also in order to learn how to protect and preserve our planet, especially in this context of global warming, climate change. Now, 71% of the Earth's surface is covered with water, making ocean-related applications ranging from transport and tourism up to food predominant in our today's lifestyle. Furthermore, there is the oceans can be seen as indicators of climate change, making ocean sciences a core ingredient of geoscience. Now, when considering ocean circulation-based applications, two main ingredients are typically exploited, which are the models and the observations. Now, roughly speaking, the models are necessary for forecast-based applications, and the observations are needed to state about the actual state of the ocean and also to validate the models. Now, combining these two ingredients in data assimilation framework provides some solutions regarding, for instance, and from a modeling perspective, the initialization of the model, and from a data perspective, the reconstruction and interpolation of gap-free maps. Now, unfortunately, several issues still persist within both these two words, and especially in the link between the two. And specifically, and from a modeling perspective, a central question, which is somehow a very fundamental one, which is how to make the models closer to the true state of the ocean. And this includes the treatment of various sources of errors, such as numerical discretization errors, model bias correction, the choice of some parameterizations that usually involve some domain expertise, there is also this issue of how to improve the predictability of the models. And this predictability problem is for sure linked to all the previous questions, but the predictability problem is intrinsically linked to the quality of the initial conditions given to the model, which also make it linked to the quality of the observations. Now there is this other kind of set of problems regarding deriving reduced order models that can faithfully catch the variability of a subset of ocean variables, both for forecast, simulation, data simulation applications. Now, from a modeling point of view, point of view, a central question is how to better explore these big amounts of data coming from either in situ networks or from satellite remote sensing observations. And this includes using and developing new data assimilation schemes that can or not rely on physical models. Another problem is how to design new sensing missions that will help our understanding of the ocean circulations, and will also help improving the predictability of our models. Now, in another word, artificial intelligence has revolutionized several signal processing fields, such as image recognition, super resolution, and signal translation. Now, the success of such techniques is mainly due, at least from a practical point of view, to the increasing amount of computational power, as well as the increasing amount of availability of observations. Now, this success of artificial intelligence techniques naturally motivated investigations within various other scientific fields, including ocean sciences, and especially in physical and satellite oceanography, where the increasing availability of model simulations, as well as increasing availability of observations of the ocean, already sets up the community with proof of concept showing that such techniques can help improving ocean models and can help better exploiting observations, and can eventually help reducing the gap between the models and the observations. Now, within both the satellite and the artificial intelligence community, a huge effort is carried in order to define and solve problems correctly using new adapted artificial intelligence tools. And from this point of view, there is this very large, interesting set of methodological problems written in the language of physics-informed AI, starting from actual ocean circulation models and how to make them better, up to the derivation of data-driven surrogate models for a subset of ocean variables. Now, artificial intelligence also kind of enriched the methodological tools used by observations guys in tackling issues such as interpolation, reconstruction, denoising, filtering of the observations. Now, this thesis, we focus on these last 2 points, and we want to answer this question of how to use data-driven techniques and artificial intelligence techniques in order to derive ocean surface models that can be useful for forecast, simulation, and data assimilation applications. We are most of the time guided by physical and mathematical considerations regarding the underlying dynamics and the observations, since we are sure that from our own experience and from the current trend in data-driven modeling, that physics-informed AI is the way to go, at least in order to tackle such a complex system, which is the ocean. Now, the general framework used throughout is a classical state-space model formulation, where we assume that there is some hidden states that are actually governing the dynamics through a differential equation. And in our context, the Z state is simply the state of the global ocean. And we also assume that we are provided with some observations that are somehow linked to this hidden state. And the general question we want to answer is how to use AI to extract models from observations that can be useful for forecast, simulation, and reconstruction applications. Now, this question is obviously linked to several problems regarding the provided observations, and specifically regarding the noise, the sampling of the observations, and the observation model age. Now, when provided with ideal observations of the state variables, or with a diffeomorphic copy of these states, and without any sampling issues or noise, several state-of-the-art techniques can be used in order to kind of reverse engineer the equations from a sequence of observations. Now, when provided with noisy observations, data-driven techniques, and depending on the type of noise, but usually data-driven techniques tend to try to work on some kind of denoised version of the observation. Now, another issue is when we are provided with irregularly sampled and noisy observations. And in this context, there is this current trend within the state of the art of investigating data assimilation schemes with learning-based approaches and neural networks to derive data-driven representations for such problems. Now, interestingly, such frameworks, so combining learning with data assimilation, actually links to classical state-of-the-art kind of deep learning variational modeling, not variational, but generative modeling, sorry, generative modeling in the framework of the variational autoencoders. Now, when considering the observation model H, a central issue is when we are provided with observations that are partially linked to our hidden state Z. In such situations, most of the previously mentioned state-of-the-art techniques do not apply, since the variability of our observations is not deterministic anymore. Now, assuming that it's coming from something higher dimensional, that it is deterministic, classical state-of-the-art modeling on partially observed system typically relies on delay embedding with regression, where recurrent neural networks can be seen as temporal propagators of these embeddings. Now, unfortunately, using the state-of-the-art techniques in the context of modeling ocean observations or ocean variables need to be considered with care to account for the proper specifications of ocean observations. Now, ocean observations are temporally sparse, either when considering remote sensing observations, where the temporal sampling of such observations will depend on the return time of the satellite, leading to huge temporal gaps in the sampling of the observations, or when considering model simulations where the resolution of model simulation products is typically days, and it misses crucial faster variability that is primordial from an identification point of view. Another issue is the fact that ocean observations are just a tiny subset of a much more higher dimensional system that involves several other unseen time-varying processes, which is the state of the ocean. Now, in order to model such observations, we need to take into account the influence of these kind of hidden processes in a manner that makes prediction possible and efficient. Another issue regarding ocean observations is the fact that these observations are irregularly sampled in spatials as well, which makes the development and the exploration of spatiotemporal interpolation techniques crucial for several applications. Now, in this work, we decided to answer these three questions regarding how to model temporal samplings, how to model partially observed systems, and how to derive reduced order models that can be useful for short-term forecast and data assimilation applications. Now, in this presentation, I will mainly focus on these last 2 points. So how to model partially observed systems and how to derive reduced order models, both for short-term forecast and data assimilation applications. Okay, so now that we presented context, goals, and general tools developed throughout this work, I dig a little bit more into the details of one of the contributions that we proposed regarding modeling of partially observed systems, where I will start by a small introduction to artificial intelligence or in the context of this work. Okay. So artificial intelligence can be seen as any technique that can mimic human-like intelligence, ranging from simple conditional structures up to much more complicated things such as deep learning and neural networks. Now, the reason behind the success of learning-based approaches, and especially in deep learning techniques, is the fact that they can approximate sufficiently well any continuous function, leading to this kind of flashy results, which are simply curve fitting. Now, I don't want to dig into this argument about the place of artificial intelligence in sciences. I don't know if you can properly call it intelligence or is it just curve fitting, but I think that AI can help develop in several fields, including oceanography, including ocean sciences, through a clean mathematical and physical formulation of the problems, in order to state about what can artificial intelligence do and what cannot artificial intelligence do in these fields. Now, quickly, how to summarize a deep learning algorithms. We start by defining input and output space. We then write a mapping between these two spaces written as a deep composition of elementary function with some weights. We then choose and define a lesson objective function that is kind of related to the job that we want to achieve using this, this model. And finally, we optimize the parameters of the model using simply gradient descent, where the derivatives of the objective function with respect to the weights is computed using automatic differentiation packages. Now, how to use this kind of tools in the context of modeling time-varying processes. And in order to kind of answer this question, I will start from a dynamical system point of view, where we are provided with a differential equation and we want to solve it in order to predict the future. And most of the time, analytical solutions do not exist, and we are obliged to use numerical integrations in order to simulate this equation. Now, from a learning perspective, we are provided with these observations, and we want to find some model that will propagate in time to a predefined time step these observations. Now, classical deep learning architectures can be used for this job, written as deep composition of elementary functions. Such architectures, however, are limited. They are hard to diagnose when things go wrong, which also makes them hard to constrain. Now, throughout all this work, we decided to use a neural ODE formulation, where our approximate model is simply a numerical integration of an approximate differential equation. And it can be seen from a learning perspective as a residual neural networks that mimics a numerical integration scheme. Such architectures have several benefits, including using all of the state-of-the-art literature on numerical integrations and dynamical systems and differential equations to kind of diagnose and constrain the optimization problems. Now, one of the questions we want to answer during this disease is how to model partially observed systems. And it can be resumed as the following. So assuming that we are provided with some observations X that are coming from some higher dimensional space, how to derive something like this equation that propagates these observations in time. Now, in order to write this equation, we need to make sure that this observation, the observation model H, is an embedding of the higher dimensional space Z, which means that this observation model needs to be one-to-one. So the projection from the higher dimensional space to the lower, to the observation space, to the space of the observations, is done without any loss of information. And this observation model needs also to be in immersion, which means that this projection, this observation model, preserves the tangent directions from the higher dimensional space to the space of the observations. Now, why do we want to care about this observation model being an embedding? It's simply to make sure that the deterministic behavior, and assuming that it is deterministic, the deterministic behavior of the higher dimensional state Z is still deterministic in space of the observations, which means predictable in space of the observations. Now, why to have such considerations in the context of modeling ocean surface variables? In order to kind of answer a little bit this question, let's consider that we are provided with some ocean surface observations, such as ocean surface temperature. Now, we know from physical oceanography that the evolution of the ocean's temperature is governed by a set of primitive equations. So in this kind of higher dimensional system, the evolution of our observations is just a tiny two-dimensional layer of a much more higher dimensional system that includes other processes and that evolves in 3 dimensions. Now, if we assume that the evolution of the sea surface temperature can be somehow decoupled from the evolution of the other ocean processes and the ocean depth, there is another source of missing information, which is the unresolved scales. The ocean variability is a multi-scale spatiotemporal process, And the provided observations has a limited spatiotemporal resolution, which is in the context of the sea surface temperature, 100 kilometers times days. And these observations will then miss a crucial faster and smaller unresolved variability that is crucial from an identification perspective. So from here, we either, the solutions to this issue is we either do some synergy study and we try to kind of add some additional observations to our initial observations in order to make, try to make our space of observations deterministic, which in the context of global ocean, of the ocean, which will pretty much send us back to global ocean circulation models that we want to avoid. Another solution is to use Takens delay evening theory, where when provided with some observations that are coming from a higher dimensional system, we concatenate lagged versions of the observations to form some kind of a higher dimensional system that reflects the deterministic properties of the unknown dynamics. Now, this technique is extremely hard to use when considering higher dimensional observations, something that is more than scalar, and the relationship between the spawned, and even if we get the correct delay evening for higher dimensional observations, the relationship between this spawned delay evening using Takens lagged coordinates and any form of dynamical system or dynamical system representations that propagates this evening in time simply does not exist. So what we propose to do is to propagate, is to search for the most appropriate space that explains the variability of our observations with respect to a given neural ODE model. And how do we do that? Is simply by giving some observations that come in from a higher dimensional space. We project these observations into another higher dimensional space that is parameterized by a neural ODE. So we assume that this higher dimensional space is deterministic and evolves using through this ODE. We then optimize both the parameters of the model, of the neural ODE model, and the initial conditions of the latent states to minimize the forecast of the observations. And this is simply the first term here in the loss function is simply minimization of the forecast of the observations, and the second term can be seen as regularization, where it makes sure that the initial conditions are not optimized independently for each time step. Now, after we finish this optimization, we end up with a geometric reconstruction of the phase space, so pretty much what Taken delay evening does, but we also end up with a dynamical system that can be used to forecast the observations in time. So we first tried this framework on the Lorentz 63 model, which is a three-dimensional dynamical system governed by these equations. And the reason behind choosing this dynamical model is we want to assess on a simple case study about the ability of the proposed framework to capture chaotic variability on the observations, which is one of the components of the ocean variability. Now we assume that we are provided with observations of the first Lorentz state, and we never assume never observe the other state, and we built our augmented space with dimensions ranging from 3 to 6. So the first experiment within this case study, we started by visualizing the spawned manifold as we minimize the forecast of the observations. So starting with pretty much noise on the latent state's initial condition, as we optimize these initial conditions jointly with the model to minimize the forecast of the provided observations, we end up with something that is pretty much diffeomorphic to the true Lorentz structure, which is very cool. Now, after optimization is finished, we can extract the dynamical model, learn dynamical model, and use it, for example, to forecast the observations from a given initial condition. And when compared to classical kind of delay embedding based techniques, our model is the only one able to capture the chaotic variability of the Lorentz. The LSTM model, on the other hand, gets stuck on some kind of periodic loop. So from here, we started having some additional investigations regarding, for instance, the attracting region of the spawned attractor. And we found out that this attracting region was very small, which is very bad. This basically means that if we take an initial condition that is a little bit farther from the observations, we end up not converging to the Lorentz attractor, but going to another limit set which is unstable. And we also figured out that we can make our model diverge to infinity by from a perfect initial condition simply by running it for long periods of time. And this is catastrophic from both a forecast and especially a data assimilation point of view, where if our analysis sends us somewhere here, we can directly make our model diverge, which also make the analysis diverge. Now we started investigating how to make our model bounded, and we figured out that there were mainly two kind of roads to take within achieving the boundedness of the proposed framework. The first category of techniques comes mainly from a learning and dynamical system point of view, where we try to regularize the training problem by making our model satisfy some stability conditions. Now, from dynamical system point of view, we don't actually want our models to be stable. We want them to be bounded but unstable, so they can reflect the chaotic variability of the observations, and this is impossible to achieve using such state-of-the-art techniques. We then figured out that by simply restricting the form of the neural ODE model to be linear quadratic, we can exactly achieve boundedness of the model through adding some energy constraint to the linear and quadratic parts of the model. And how do we achieve that? Sorry, so starting from the first neural limiting formulation, making it bounded, which also makes it generalized to any initial condition, even if given from very far from the observations, can be simply achieved by restricting the form of neural ODE model to be linear quadratic, and by adding some energy constraints on the quadratic terms and linear terms of linear quadratic model. We then tested this new bounded formulation of the neural limiting model on, retested it on Lorentz 63 case study, where when compared to the unconstrained version, the constrained version now can't properly simulate Lorentz 63 dynamics given a perfect initial condition, doesn't diverge after long simulation times, and most importantly, even if given an initial condition that is farther from the observations, we still converge to the Lorentz attractor and stay there to infinity. We then kind of shifted our focus to the modeling of sea level anomaly dynamics from the Western Mediterranean operational forecasting system, the WMOP, which is a high resolution regional ocean model that have a spatial resolution of 0.05 and with a daily temporal resolution. And the considered case study region in the south of Mallorca, and we used the as training data the years from 2009 to 2014, and we tested our approach on the year 2015. So we generated two neural ending simulations starting from slightly different initial conditions. And when comparing these simulations to the true WMOP simulation, the proposed framework can achieve a good short-term forecast. It can keep simulating realistic spatiotemporal structures given in the WMOP to infinity. And interestingly, even if the initial conditions are slightly different, the true neural limiting simulations diverge from each other after a finite amount of time and they start simulating their own version of the future. I'll let you watch this. Okay, so the main takeaway messages of this part is that the fact that we proposed a new dynamic limiting approach that can be used for the modeling and simulation of partially observed systems. Now, what is interesting about the proposed framework is that we do not assume any prior knowledge on the hidden states. And when compared to classical, for example, state-of-the-art delay limiting technique, the augmented space is optimized to minimize the forecast of the observations, which makes the latent states kind of implicitly linked to what we do not observe, since they are here to minimize the forecast of the observations. Another aspect of the proposed framework is that it's bounded by construction, so it can make possible the simulation of long-term dynamics. Okay, so let's pass now to the second kind of main contribution of our thesis regarding reduced order models for short-term forecast and data assimilation applications. So given the following state space model, the resolution of the dynamical equation for short-term forecast and data assimilation of subset of ocean variables is extremely challenging, mainly due to the dimensionality of the state Z. So the main goal of this work was to derive reduced order models that can faithfully catch the variability of a subset of ocean observations. Now, when considering the previous neural imaging framework that we presented like a couple slides ago, we had these reflections regarding the relationship between the dimension of the embedding and the parameterization of the neural ODE model, and how to optimize both these two parameters in order to achieve a good short-term forecast without necessarily caring about the ability of the model to long-term simulate the dynamics. We then focused on linear parameterization, since they provide the theoretical link between the dimension of the embedding and the parameterization of the model written in the language of the Koopman operator. And these Koopman representations, even if they are linear, they can provide a good short-term forecast for chaotic dynamics. They can also provide a perfect linear translation of some of the nonlinear dynamics, and they allow us to use very simple state-of-the-art Bayesian filtering techniques, such as the Kalman filter, which makes them extremely valuable for data assimilation applications. Now, so quickly, what this Koopman operator is about, it's simply, so assuming that we are provided with a nonlinear dynamical system F that propagates some state x in time, the Koopman operator KT propagates linearly in time a collection of observables of the state. And those observables can be infinite dimensional. And this framework is actually quite old, and it was up until recently that people are trying to investigate linear-based approaches and data-driven techniques to try to find a good finite dimensional approximation of this operator that can be useful for forecast, simulation, data assimilation, applications, and control. Okay. So given the following state space models, the modern state-of-the-art techniques on data-driven derivation of Koopman operators can be decomposed into three main categories. The first one, so the dynamic mode decomposition, simply computes the best linear fit that propagates the observations in time. The extended dynamic mode decomposition computes the best linear fit that propagates observables of the observations in time. And those observables are computed based on a parametric set of functions. For example, polynomial observables are used for the linearization of equilibrium points, and delay embedding observables are used usually for the linearization of nonlinear oscillation and quasi-periodic signals. There is also a recent interest in using deep learning approaches in order to derive observables from neural network models that can be propagated linearly through a linear model. Now, the issue within all of these state-of-the-art techniques is that they do not account for missing processes. They only work on the observations, or they use takens. Now, another issue is the fact that the augmented space, so the space of the observables, actually depend on a predefined family of functions, where the Koopman observables may be missing. The suitable observables may be missing. So in order to tackle this issue, we propose to, pretty much similarly to what we did in the neural imaging model, so given some observations that are coming from a higher dimensional system, we project these observations into a higher dimensional space that is parameterized by a linear ODE. We then optimize both the parameters, the Koopman modes, so the parameters of the metrics, and the observables to minimize the forecast of the observations. We then tried this framework into the linearization of various dynamical regimes, including equilibrium points, nonlinear oscillations, chaotic dynamics, and stochastic dynamics. But the main case study I want to show you today is regarding the forecast of large-scale, extremely large-scale kind of seasonal variability of sea level anomaly from the WMAP. So here, starting from the left to right, we have the WMAP simulations, the projection from an EOF basis. So this is the best forecast we can achieve, and the Koopman forecast, so our proposed framework. And actually, we do lose the fast and small scales variability, and simply because it's highly chaotic and can be modeled using a finite dimensional linear model. But we do catch kind of the extremely high, large scale variability of the dynamics. It stops at 50, don't worry. Yeah. Okay, we then shifted our attention into spatiotemporal interpolation of sea level anomaly data coming from long track observations. And these observations actually involve extremely high missing data rates, making the effective resolution of a classical interpolation products using classical state-of-the-art techniques such as optimal interpolation very high. And within the ocean community, there is an interest in unfolding smaller scale variability, which led to both investigating new sensing missions and exploring learning-based approaches in order to spatio-interpolate such observations. Now, the spatio-temporal sea level anomaly interpolation can be defined as, given some sea level anomaly observations, how to define an inversion method that will put these observations into a regular grid. Now, beyond classical optimal interpolation technique, learning-based approaches can be divided into three main categories. The first one, so plug-and-play schemes, simply try to optimize a dynamical prior that propagates these observations in time and then puts this dynamical prior into classical data assimilation schemes such as the ensemble Kalman filter and stuff like that. So these techniques are extremely versatile since they do not depend on the observation sampling. Now, regarding the sea level anomaly, for example, this observation sampling is known and it corresponds to the orbit of the satellite. And including it in our interpolation method can help achieving better results. The other category of method comes mainly from a learning community, where we try to find a model, a parametric model that will directly map these observations into a regular grid. Now, these techniques take full advantage of the observations and their sampling. They are, however, extremely hard to diagnose. So what we proposed is to take some ideas from both these two words and to implement a sequential filtering scheme, so the Kalman filter, in an end-to-end setting. And how do we do that? It's simply by writing a Kalman filter with as a dynamical model, the augmented Koopman framework that we just presented, and we optimize the parameters of this dynamical model based on a reconstruction cost. So given some observations, we do a reconstruction of the observations. We then compare this reconstruction to some ground truth, and we optimize the parameters of the model to minimize the reconstruction error. We then tried this framework on simple OSSE-based case study built on the WMAP simulations, where we divided the WMAP simulations into training and testing sets. And we then generated realistic and long-track observations from a 4-altimeter configuration in 2014. And when comparing the proposed framework to classical optimal interpolation and to other data-driven plug-and-play schemes such as the local analog data assimilation, we see that we achieve a very good reconstruction when comparing to classical optimal interpolation, and we slightly do better than the analog data assimilation technique. So this is a visual reconstruction example on February 19, 2015. So in the test set, the first line here is the ground truth the gradient of the ground truth and the observations. The second line is what does the optimal interpolation, and the analog data assimilation, and in extreme right, the proposed framework. And we see that our proposed models do much better than the optimal interpolation, simply because optimal interpolation is known to smooth small-scale structures. And we do kind of slightly better than analog data assimilation, which can be seen through the visual analysis of the gradients. Okay. So the main takeaway messages of this part is that the proposed reduced or linear reduced order models can be used for the identification of linear approximation of high dimensional nonlinear dynamics. And this framework is actually relevant for the forecasting of short-term chaotic dynamics that contain some periodic and quasi-periodic modes. It can lead to perfect linear translation of some dynamics, such as smooth periodic and quasi-periodic oscillations, and single equilibrium points, single nonlinear equilibrium points. And the linearity of this model also makes it relevant when considering spatiotemporal interpolations and more generally data assimilation applications. So moving to the conclusion, I think that the work carried during this series shows just a little bit the potential of using artificial intelligence and learning-based and data-driven based techniques in the modeling of ocean surface variables, both for forecast simulation and data assimilation applications. Now, I do also think that all the work did during this series need to be more investigated in order to answer questions regarding the ocean variability and how to understand our ocean through, for example, tackling issues such as how to improve ocean models using what we proposed here and how to make them match the observations. Now, regarding the perspectives and when considering data-driven modeling of ocean-related variables, I think that several improvements can be done in order to kind of upgrade the proposed frameworks in this disease to include and to take advantage of several aspects that will lead to a better understanding and better modeling of ocean surface observations, such as, for example, this question of how to model fast scale. These fast scales, I think that we can find the signature on the observations, so how to include them explicitly on the models. We think that we want to think that the augmented neural ODE formulation have some information of these fast scales in the necessary for forecast, but how to prove it and how to include this modeling explicitly in order to, for example, improve your forecast of a large scale. Other issues regarding how to explicitly constrain chaos within the proposed models and how to deal with and model stiff phenomena in the observations. Now, a more central question is how to transpose all of the proposed methodological tools and knowledge carried during this disease into the modeling of real ocean observations. And I think that it can be answered from three different angles. The first one is, for example, using data-driven modeling, so pretty much what we did during all this disease. So with the extra concern of how to deal with irregularities in the observations. Another road to take is to start from kind of reduced order already there physical models and try to improve them with learning missing physics, closure terms, some forcings in order to make them match the observations. Now, some thoughts towards artificial intelligence and its place regarding global ocean circulation models. I think that, and this is very my naive point of view, I'm not a specialist in ocean modeling, but my naive point of view tells me that I think that such frameworks, artificial intelligence, ocean global circulation models, should be envisaged to be working together online in order to make the ocean models closer to the observations. And such a thought will necessarily raise several questions regarding how to, for example, make an ocean global circulation model differentiable, and is it possible to be differentiable, and what is the backward pass in such situations, what is its cost, is it tractable, go to neural solvers, and it actually raises an extremely large amounts of question that maybe I'll be happy to answer at some day. Okay, so this is some bibliography. That was my PhD presentation, and thank you. I'll be happy to answer some questions.
Thank you, Said, for your very nice presentation. So now the committee is going to ask you some questions. So
Sure.
the first one